So continuing with our discussion of charges, we're going to talk about distributions of charge and the law that governs these being Gauss's law. And here is an old German mark banknote here with Gauss on it, being the famous scientist that he is, and we're going to cover him with a uniform distribution of charge. Remember, when we're dealing with like charges, they always repel. So a uniform distribution is not an unusual thing to see, as all charges will try to move as far apart as they can. Now, when we're dealing with these charges, we are always dealing with an electric field resulting from these charges. And Gauss's law can be used to actually quantify the amount of electric field running through an area or surface that we choose, that we can define mathematically. But why do we care about the electric field as much as we actually do? Well, in the modern world, the electric field has become ever more important. If you think about such things as wireless communications with a laptop or phone, these rely on very fine, very well-tuned signals to relay data. If you look around you at the lights and look around you at all the electric systems that are in your home or classroom, then you realize that there's a lot of wire in them. And if they are unshielded, they will actually be subject to radio frequency interference. They will actually put out RF interference. Take a look at a computer transformer or other electronic device, and you often see recommended by the FCC to accept electronic interference. That's that it will accept interference rather than cause it. So we often require a lot of shielding around modern wiring and modern electronic systems so that they don't interfere with our sensitive wireless communications, which are really just electric fields that we can pick up with our devices. As a bit of a recap, remember Coulomb's constant was K, and this was 1 over 4 pi epsilon 0 and gave us roughly 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. This 4 pi was the result of a point charge in 2 dimensions, 1 in 2 pi in one direction, 2 pi in the other, to give a sphere. Epsilon 0 was the permittivity of free space, how much electric field was allowed in any one particular region. And we looked at Coulomb's law and the force between charges through F equals K Q1 Q2 over R squared, where the K we were just dealing with was what we were looking at in the previous slide. We also had the electric field strength. This was E equals V over D for the case of a capacitor, F over Q for the case of a charge, or K, magnitude of Q, over R squared. And remember, K here is the 8.99 times 10 to the 9. And this was how we really applied it, in terms of looking at the Coulomb's law for a pair of charges. Here you could have two charges of magnitude 6 and 3 times 10 to the minus 6 coulombs respectively in a 0.03 meter separation. And you could calculate the amount of force between these two charges. So that was a bit of a recap. We want to get into talking about Gauss's law. And here's a picture of Carl Friedrich Gauss, who lived from 1777 to 1855. He was a German mathematician and made a lot of different contributions to mathematics and physics. And Gauss's law is one of those that we'll look at. Gauss himself was quite a miserable person and actually discouraged his children from going into science because he didn't want them to have a law themselves which would supersede his own Gauss's law. But personalities aside, his contribution to science was quite strong. Gauss's law can help us to calculate the electric field due to a distribution of charge. Now, Coulomb's law is very, very useful if we're looking at, say, two charges, and then trying to find, say, the net electric field or the net force between 2 or 3 charges. And remember, when we talked about superposition, we would have to calculate the force or electric field between 2 charges and then add it to another 2 charges, say Q1, Q2, and Q3. We would have to do K Q1, Q2 over R squared, K1, Q3 over R, Q1, Q3 over R squared, and sum them together to get a total answer. And that works with a limited number of charges. You wouldn't want to do it for 4 or 5, more than 4 or 5 charges. Now, Gauss's law is a great way of looking at a distribution of charge where you can have tens, hundreds, thousands of charges and look at the electric field due to them. So Gauss's law really allows you to do the same thing as Coulomb's law, but is a lot easier when you're dealing with large numbers of charges. We will limit ourselves to charge distributions that are very symmetric, and you'll see what I mean by symmetric as we go through. Now we've already seen this, but just as a reminder, the electric flux, or phi, are given as a symbol because E is already gone for electric field. So here's phi for electric flux, is the number of electric field lines which pass through a given cross-sectional area. That's known as the flux. And here we have a cross-sectional area. We have an area A, which is one side times the other side, and we then see a group of field lines, electric field lines, running through it. The flux is how many of these field lines there are running through this area. And that's what we're going to attempt to quantify. So the electric flux, or phi, is a measure of how much an electric field wants to push through or flow through some surface area. And this is dependent on what's in that surface area partially, but here we're going to deal with essentially free space for everything we look at. And we care about flux because it makes a lot of our calculations much easier. So when we talk about electric flux, we say that phi, the electric flux, is equal to the electric field strength E times A. Again, this is a similar diagram to the one we saw before. Here's some area A lying in an electric field, which is these pinkish purple arrows. Phi will be E times A, and then depend on the actual orientation of this area lying in the electric field. So here it's intercepting the majority of the electric field lines because it's perpendicular to them. If it was lying down in the field, it would be intercepting no electric field lines. Consequently, we have this cosine theta component here, which tells us how your area that you're interested in is oriented relative to the field. So theta is the angle between E and A. So the flux through a surface is a measure of the number of field lines passing through that surface and is dependent on E, A, and cosine theta, how the field is oriented relative to your surface. The maximum flux will always be when most field lines are being intercepted, when the field lines are running this way and the area is oriented 90 degrees to your electric field. So your flux is heavily dependent on the orientation of your chosen area. So phi is EA cosine theta, as we already said. And so that means if we take a look at our surface here as it lies in the field, 90 degrees to the field, it will intercept the maximum amount of lines. If we change the orientation of our field, it should intercept less lines with increasing theta, with increasing angle. We do often have this unit vector A that tells us the orientation of our particular field. So here's our electric field. If we have quite an extreme change in the orientation of the field, you should see that it intercepts less electric field as your angle increases, until the actual area is lying down flat in the electric field at which point it actually intercepts no electric field whatsoever. So the easiest case is where we say the electric field, which I will always present you with a uniform electric field, is uniform, and the plane is perpendicular to the field. That means it's standing up in it. Its area is oriented 90 degrees to the field. And that's really the simplest case. So our electric flux, phi, is equal to EA, depends on the strength of the field here and the area. If the plane is not perpendicular to the field, then phi will be EA, which will be EA cosine theta. Often, a unit vector of A is defined which sticks out of the surface and tells us where the normal unit vector is pointed. This is very important for some of the examples we're about to see. So let's take a look at a few problems here. These are relatively simple, and we don't really want to look for the mathematical answer for these. We just want a quick answer. So let's just think about the flux of the electric field E through each of these surfaces. So if we look at case A, you really want to ask yourself, is this going to be a high value of phi, a high flux, or a low one? Well, in the case of A, we can say that phi will definitely be a maximum, the area being perpendicular to the electric field. In the case of B, now we're looking at the area lying down completely in this electric field. Never assume that your area has a thickness. These are mathematical constructs. We can define our area to be anything we wish to be. It does not have to be physical. So don't worry about it having a thickness unless you're told to. So this is a two-dimensional area. So if it's lying down in the field, essentially 180 like that, we will end up with a situation where it's minimum or zero. Anything between these two cases, anything other than the maximum or minimum case, and you will have to apply EA cosine theta. So for C, we would have to calculate phi through EA cos theta, and this theta is going to be the angle that is made between a normal coming out of the surface here straight forwards and the electric field lines. So let's take a look at a problem. Here we have a 4 centimeter square. So our area, we have a 4 centimeter square here, so we can calculate our area. It's sitting in the XY plane in a uniform electric field. The electric field is given by this vector. E is equal to 2I plus 3J plus 5K. We're asked to find phi. Immediately, you should be thinking that phi is equal to EA, and we know this is true. But what component of phi of E is going through area A? Well, we know E is equal to 2I plus 3J plus 5K. Our surface is oriented in the XY plane. That means it's actually going to be sitting in the XY plane, which is the 5K direction. So our area was 4 centimeters on one side. So we're looking at an area, length of 4 centimeters one side. So area is 4 times 10 to the negative 2, always work in meters, times 4 times 10 to the negative 2, which will give us 16 times 10 to the minus 3 meters. This should, of course, say square meters. Phi is going to be E times A. Now, as we said, this is in the XY plane. That means it's intercepting all of the electric field through the K or Z direction. That means phi is equal to E times A, which is equal to 5 newtons per coulomb times 16 times 10 to the minus 3 square meters. This will give us 0.008 Newton meters squared per coulomb. Let's take a look at another one. Here we have a square measuring 3.2 millimeters on a side. It's immersed in an electric field of 1800 newtons per coulomb. The field lines here are making an angle of 35 degrees normal to the surface, and we want to find phi through the surface. In this particular case, you're given one side of the square, you're given an electric field of 1800 newtons per coulomb, and we're given an angle. So you're being led towards what you should do and the procedure you should follow. Physically, this is what's happening. The electric field is coming in here and making an angle of 35 degrees to our surface of interest. So this means phi will be equal to EA cos theta. Remember, our area is actually going to be 3.2 times 10 to the minus 3 squared times cos 35, which will give us 1800 newtons per coulomb times 1.02 times 10 to the minus 5 square meters times cosine of 35, whatever the cosine of this angle is. That will give us 15.1 times 10 to the minus 3 Newton meters squared per coulomb. So that's how we can calculate the electric flux on a surface. It's the net electric flux through a surface is directly proportional to the number of electric field lines passing through that surface. Let's take a look at a case where we're looking at a three-dimensional system. So in this case, we want to look at the electric flux through a cube and quantify the electric flux through this 3D surface. So let's visualize this system correctly. Here we have a cube which has multiple faces, 1, 2, 3, 4, 5, and one on the back, which would be 6. So this is essentially the same as a dice. You can count the faces if you wish. We define unit vectors A1, A2, and A3, A4, and you could have an A5 and an A6 on the back and front if you wish. We do this deliberately because our electric field is running here from the back face A1 through the face A2. Now, why do we use these unit vectors? Well, that means the unit vector A1 is going into the electric field, and the unit vector A2 is going in the same direction as the electric field. This is very important because it tells us how the different faces of the cube are aligned with the electric field. It tells us what's coming into this space and what's going out of this space. So our electric field is starting this side and running through this cube, in through face A1 and out through face A2. So let's add the 6 faces of this particular cube. So the flux through A3 and A4, because these are the top and bottom of the cube, will be perpendicular to the field. They'll be lying down inside this field. They're going with the field. They're not intercepting anything. That means the electric field running through them is essentially 0. The front face, this side, and this back face here are also 90 degrees to the field. That means, again, the electric field running through those faces is essentially 0. So the only flux we have, the only place where the electric field is running through a face of this cube because of the orientation of this cube, is the electric field is running through A1 and out through A2. So it goes in A1 and out A2. That means that phi will end up being EA cos theta for both cases. It will be plus EA for A2, and it will be minus EA for A1. That's because A1 is going against the field in the negative opposite direction, and A2 is going with the field. So if we add up the flux for this system, the net flux will be EA plus negative EA plus nothing for this face, nothing for this face on the back, nothing for this face, and nothing for this face. So our phi net, our net flux, comes to a total of absolutely nothing. And this might seem like a pointless result because the answer is 0. But what this is telling us is all the electric field that's coming in through A1 is leaving through A2. All the flux through this cube is equal. The electric field is free to flow through this cube. Now, if the flux was non-zero, that would mean that electric field was being lost in this region, and then we could find out why. Perhaps there was a metallic object in here. Perhaps there was something interfering with that electric field in that cube. But here, our phi is 0. So we know that all the electric field incident on the cube is all the electric field exiting the cube. Now we can do this for a number of different geometries, and I will always give you a symmetric geometry if I expect you to do this. And think about the kind of three-dimensional shapes you might see that would be relatively symmetric, and there is only a limited number that you can see. If you're also talking about an area, imagine the kind of area we could define. We could define a square, a rectangle, we could define a circle. So we're going to stick to basic geometric shapes. Don't expect to see any particular complicated pyramids or other weird shaped objects in this particular class. So let's take a look at our flux through this cylinder. So here we have a cylinder lying in our electric field. The electric field is coming in this end and out of the other end. We can define two areas here. One area here on this end of the cylinder and another on this end of the cylinder. Two circular areas. There's also the outer skin of the cylinder that we should consider. So let's think about the direction of the electric field from left to right and which parts of the cylinder are truly intercepting the electric field. Well, the outer skin of the cylinder will be parallel to the field. So this outer skin of the cylinder will actually equal an area of pi r squared times L, but the outer skin of the cylinder is parallel to the field. So its total electric field here that's incident on it is 0. So that will give us an electric field of nothing. Let's consider now the end caps, the circles at either end of the cylinder. Well, this end cap is going into the field. That means our area is going to be negative. So the area of a circle that's intercepting this particular electric field is pi r squared. Attaching our negative gives us E times negative pi r squared. This A is simply this unit vector A here. Hats are difficult to put on in PowerPoint. That means this end of the cylinder will have pretty much exactly the same expression, but in this direction it's going with the field. So phi here is positive pi r squared times E. So that means the total flux of our system is going to be negative pi r squared plus positive times E plus E times pi r squared positive. So that gives us negative E pi r squared plus E pi r squared, which cancels everything out and once again comes to 0. So here we're using Gauss's law to prove that the electric field through these systems is 0, is uniform throughout and is not disrupted. So even though this is 0, it is quite a significant result. So Gauss's law is a flux calculation, And we can build any Gaussian surface we want. A Gaussian surface is essentially imaginary. It's a mathematical construct. So don't think about what it's made from, how is it constructed. It's really a way of quantifying how much electric field is running through some part of space and modeling that electric field with the flux to know how strong our system is. So Gauss's law only applies to closed surfaces. You have to have some area that is completely enclosed or some particular shape, three-dimensional volume, which is also enclosed. And it really, as we said, it can relate electric flux to a charge distribution that creates it. Now I'm going to show you something I don't usually show you, and that's actually an integral. And that's actually a calculus function, but essentially it's a sum. You will have to employ this, but it's good to see this because this is what's really going on. The net flux is the total sum over an area, over a complete surface area, multiplied by an electric field. And this little circle really saying that this is an enclosed summation, an enclosed integral. This will equal Q that's enclosed in our entire area divided by epsilon 0, the permittivity of our free space. That's how this is derived, but this is the version of the formula that you will employ the most. Phi, as we've already said, is EA, or EA cos theta, but this can also equal Q enclosed in our surface divided by epsilon 0. And that means if we have a set amount of charge in or on our surface, it will result in a certain electric field with a certain flux. That way we can relate the flux to the electric field to how much charge is present in our Gaussian surface or on our Gaussian surface by saying phi is EA equals how much charge we've got Q enclosed over epsilon 0. And this is extremely useful, figuring out how much charge we have in an area. And this is often where these 4 pi factors that we've discussed before might come into effect. So here is a point charge plus Q. Here's our point positive charge, and here we have some radius r that we've defined. So here we have a spherical Gaussian surface. And you've seen this before. KQ over r squared. And this is where this really comes from. This is the flux due to a point charge in a three-dimensional sense. So here's our A, our area, and here's our electric field E coming uniformly out in all directions in a perfect sphere from Q. Flux phi net will be KQ over r squared. So if it's KQ over r squared, essentially this is multiplied by A, as we said. A is a sphere here. It's coming out in a spherical distribution. So the surface area is really A equals 4 pi r squared, representing 2 pi in this plane and 2 pi in this plane. That means phi net is KQ over r squared times 4 pi r squared. Now remember, we can rewrite Coulomb's constant in terms of the permittivity, in terms of epsilon 0. So Coulomb's constant K is 1 over 4 pi epsilon 0. It's a spherical function. Now that means, once we substitute in, that phi net becomes KQ over r squared times 4 pi r squared. With some cancelling here, you can see we have our r squared here. We know that K is 1 over 4 pi. That will essentially cancel our factors of 4 pi, cancel our r squareds, and give us phi as Q over epsilon 0. So EA is essentially equal to KQ over r squared times 4 pi r squared, which is 4 pi KQ. Epsilon 0 will then become 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. And that's where our permittivity of free space comes from. How much electric field is present due to a charge per unit in a medium, epsilon 0. and the permittivity of any material relates to a material's ability to resist electric field. So in this way, we can figure out which materials are best for shielding electric fields, for say insulating wires to prevent interference with communications. That's a practical application. So Gauss's law is very versatile. Gauss's law can be used to find the electric field at some point relative to a known charge distribution, or find a charge distribution if we know the electric field. And this is kind of what I want to talk about next. And that's what happens if we have a sphere of charge. If we have a sphere, so think of this particular object here as a ball, essentially. And instead of being a point charge, what we have is a ball with a radius a. So here's our sphere. And we're going to start out right at the center of this sphere and then move outside of this sphere, penetrate its skin, and then keep moving through space. Now, this sphere has charges spread all over it. And as we've said, charges will always repel and give us a uniform charge distribution. So what we essentially have here is a spherical distribution of charge. Now, as we start at the center of this particular sphere and move towards its radius, so starting in the middle and we're moving towards one side of it, what we'll end up with is a change in electric field. When we're at the center, we'll have equal participation, equal contribution in our electric field from this side, this side, this side, this side, due to the symmetry, essentially cancelling our electric field. So our electric field is 0 at the center of the sphere. As we approach the outer skin of the sphere, our electric field will start to increase. So E will be equal to kq over a cubed r. Now, as you can see, here is A, and here is the edge of the sphere. As we penetrate the sphere and move through space, we actually see that the entire sphere obeys E equals kq over r squared. And that should be familiar because that is actually the electric field due to a point charge. That means when we're outside of a sphere of charge, a spherical distribution of charge, we should see it essentially in its contribution to the electric field, and indeed the force that it inflicts on a charge near it, as a point charge. So all of this charge that's in our spherical distribution behaves as it's concentrated at one tiny point in space once you're outside of it. If you're inside of it, it takes on different rules and has kq over a cubed. So any spherical distribution of charge essentially behaves like a point charge, which is something we've said before and something we can now stick by. Another distribution of charge that we can see is referred to as a line charge distribution. So here, instead of looking at an area, what we're looking at is a long line, and this could essentially be modeled by something like a wire. And here we have a very long cylinder, and we have charges spread equally along it. So we have a uniform distribution of charges, but now just in a line rather than spread out on an area. We can find the electric field here some distance r, so we can see like a cylindrical sheath running around the outside of our particular line charge. Now, a line of charge is given by a very specific symbol. It's given by lambda, and lambda, when you see that, is essentially charge per unit length, not charge per unit area, but charge along a length. So lambda is always a line charge. And this value here, lambda, is charge per unit length, coulombs per meter. And here we're looking at the top of essentially an infinite wire. So the wire is coming out of the screen towards you and putting out radial electric fields. Now, if this was negative, this would be the same field geometry, but these lines would be going inwards. The arrows would be pointing into the wire instead of out. So let's take a look at our line charge. So if we're looking at a line charge, we're looking at a radial solution for the electric field, as we saw in that previous slide. Every cylindrical point on the Gaussian surface will have some magnitude E. And E here is a positive charge, so it's running outwards through our Gaussian surface, which makes our signs a little easier to deal with. Any cylinder will have some area here of 2 pi r, which is essentially the area of a circle. The area of a cylinder, remember, being 2 pi r L. We'll have no flux through the end caps. Remember from our previous slide that our electric field is coming out sideways. So it's 90 degrees to every point on this cylindrical surface. So there's no flux through the top or bottom of these caps, as the electric field is radial in nature, and the wire here we're going to say is infinite. And this is quite true, because when we're talking about the size of an electric field coming from a proton or an electron or some other such charge, we're talking about a very, very small size compared to the length of a wire. So this becomes a reasonable approximation. So we consider the length of our wire to be infinite, and the electric field is parallel to the end caps at all times, giving us only an electric field through the cylinder wall, I should say. So the charge that's enclosed here by our Gaussian surface is essentially lambda, the charge per unit length, or here the height, which is essentially the length. So charge per unit length times length. So lambda is Q over L, charge per unit length, in coulombs per meter. Now we know our expressions for phi and Q enclosed, so epsilon 0 phi is equal to the charge enclosed in this particular surface. That means we also know what phi is. Phi is 2 pi r h from our previous slide. So epsilon 0 E times 2 pi r h is equal to lambda h. Rearranging, we can say that the electric field is the line charge, lambda, which is essentially in coulombs per meter, over 2 pi r, which is the area of our cylinder, times h. 2 pi r L, the area of a cylinder, for any line of charge in a case like this. So let's carry on looking at charge distributions. And we've previously talked about conductors, mostly in the context of discussing such things as heat and radiation and ductility and such things as this. However, we are going to come into talking more about electrical conductors as the course continues. An insulator is something that likes to hold on to charge. Rubber, for instance, likes to hold on to charge, does not like to permit charge to move through it easily. They have excess charge essentially being stationary upon them. Conductors have free electrons and correspondingly different electrostatic characteristics, meaning that charge can move much more freely over or through them. So, when we're talking about electrostatic equilibrium, this is a state where we have no net motion of charge. Most conductors, when they're left alone, go to electrostatic equilibrium. So go and touch a piece of metal anywhere in your room and you shouldn't get a shock from it. There should be no current set up from it due to a lack of electric field, net electric field, and a lack of potential difference. So any conductor which is in electrostatic equilibrium should abide by the 4 following characteristics. The electric field should be 0 at all points inside the conductor, and that doesn't matter if it's solid or hollow. If it's an isolated conductor carrying excess charge, the excess charge will sit on its surface. Number 3, the electric field just outside a charged conductor is 90 degrees to the surface and will have a magnitude that we've seen before of sigma. Now sigma is a charge per unit area over epsilon zero. So sigma is a surface charge density. This is the amount of charge Q per square meter. So coulombs per square meter. That's sigma. Finally, we'll have a surface charge density, which is biggest where the conductor is, and this is most unscientific, most pointy. So if we think about something like an electron microscope, it actually employs an extremely sharp point. That's because it can actually concentrate more charge in something that comes to a very fine point than it can something that comes to a blunt or flat point. So very, and I hesitate to use this, pointy things have more charge concentrated within them at that particular point due to their geometry. But in general, what we've said is for an electric field inside a conductor, it's zero. If we take this particular conductor, say a piece of metal, and immerse it in this electric field, it will be affected by the electric field in that the electric field will flow around it. So the electric field inside here is zero, but the electric field around it is non-zero. The electric field will have the result of polarizing the system and creating negative charge on one side and a net positive charge on the other. So if we put any conducting slab in an external electric field, the field inside the conductor, if it were not zero, then the free electrons in the conductor would have this force and you would end up with them accelerating around. Those electrons essentially would be moved by the electric field. So before an electric field is applied, free electrons are essentially distributed throughout a conductor. When an external electric field is applied, the charges will immediately redistribute themselves incredibly quickly until the magnitude of the internal field equals the magnitude of the external field. So if there's no external field, you'll have a random distribution of electrons, essentially giving you a net electric field of zero. There's a net electric field of zero inside the conductor. So when we turn on our electric field, it reorganizes all those electrons, and that redistribution takes about 10 to the negative 15 seconds. And that then reorganizes the system, and you end up with another net electric field inside your conductor of nothing. So when we deal with the electric field inside a conductor, charge only sits on the outer surface. It does not sit on the inside of your conductor. So there's no net flux through this Gaussian surface. As the Gaussian surface is close to the actual surface you desire, there's no charge inside of it. So here's our Gaussian surface, here a weird amoeba-shaped blob. We're not necessarily going to ever look at a shape like this, but our charge, our negative charge here, is localized on the outside of it. So let's take a look at an actual practical image. When we look at our electric field here and the direction and magnitude, here we have a plate with an electric current flowing through it, an electric field being set up by this plate, and this essentially is real system. So this is a fluid with lots of conducted particles set into the fluid, and these two conductors have been put into it. So here we've got an electric field set up between this ring and this plate, and you can see the field lines running from one to the other in the similar sense to the diagrams that we've seen before. You will notice that inside of this ring, inside of this circle, there's a random distribution pattern essentially of the particles inside. They are not aligning with an electric field as per the particles outside of the circle. So there are no field lines inside this cylinder that's been placed in this fluid like there are between the cylinder and the plate on the outside. So the electric field inside the cylinder is essentially zero. Outside, it's non-zero. The charges are residing on the outsides of the conductor. So the electric field inside a conductor is 0. The electric field outside is some non-zero value, and our charge distribution remains on the outer surface. And this is particularly useful. This means if we look at a situation we talked about before, if you have a cylindrical aircraft such as this, and we're sitting inside of that cylindrical aircraft and it gets struck by lightning, the electric field from the lightning does not propagate through the aircraft and electrocute everybody inside. The charge runs down the outside of the aircraft through the path of least resistance and discharges into the ground. There is a 0 electric field through the inside of the aircraft. That would of course change if you happen to be in contact with the outer metal skin of the vehicle, and any wiring or equipment in contact with the outer metal skin would of course experience a current running through it and charge running through it and would be shocked. And you can see this kind of experiment that if you happen to be in a very severe thunderstorm and you're worried about being struck by lightning and have your car nearby, you can sit in your car. Cars are relatively good conductors of electricity, and here from this 1950s experiment you can see this man sitting inside of this car, and we have a very large generator here, static generator, and there's a very big static charge built up on this, and they are discharging this spark through this car, and here at the bottom of the wheel you can see the spark going to ground. Essentially the charge is traveling down the outside of the car and then discharging into the ground, and the electrons are being dissipated into the earth. So if you sit inside your car and the car is struck by lightning, it may burn out some wiring or things in contact with the metal, but it shouldn't shock you, provided you're not in contact with the metal shell of the vehicle. This, of course, doesn't apply so well to modern cars, which have less and less metal within them. Here's a relatively modern Audi that suffered a lightning strike, and as you can see, large sections of it have actually been melted off, mostly the plastic components. So the electric field inside our conductors is 0, and we can actually specify any number of different types of Gaussian surface through our conductive pathways. So here we have an actual cylinder set up through this unusual shape. And if we apply Gauss's law, phi will of course be E times A for this surface. And the complexity of the surface, of course, as I've said, could vary. I'm not going to give you teardrop shapes. I'll give you relatively simple shapes. But E here is sigma charge per unit area over epsilon 0. If we substitute this in for E, then what we'll end up with is sigma A over epsilon 0. So take a look at any number of these variations and substitutions. So in terms of Gauss's law, let's take a look at a couple of examples. Consider a thin spherical shell here of radius 14 centimeters with a total charge of 32 microcoulombs distributed uniformly on its surface. Find the electric field. 20 centimeters from the charge distribution. Well, we have 20 centimeters and we have a charge of 32 microcoulombs. This one should be relatively simple and is a simple application of kq over r squared. K is 8.99 times 10 to the 9 as always, and microcoulombs are 10 to the negative 6 coulombs. So 8.99 times 10 to the 9 times 32 times 10 to the minus 6 over 0.2 squared is equal to 7.19 times 10 to the 6 newtons per coulomb, or meganewtons per coulomb. Finally, let's take a look at a square plate of copper with 50 centimeter sides. There's no net charge and it's placed in a region of uniform electric field of 80 kilonewtons per coulomb. That field is perpendicular to the plate. Let's find the charge density of each face of the plate and then the total charge. Remember, charge density is given by sigma, charge per unit area. So sigma here is going to be 8 times 10 to the 4, this is 80 kilonewtons, times 8.85 times 10 to the minus 12. This is going to be our overall system here, sigma. This is going to give us 7.08 times 10 to the minus 7 coulombs per square meter. Now Q was equal to sigma times A. This is going to be equal to our 7 times 10 to the minus 7 coulombs per square meter times however many square meters we have, which turns out is 0.5 meters squared, which will give us 177 times 10 to the minus 9 coulombs, or 1.77 times 10 to the minus 7, or 177 nanocoulombs.